Hi. Next, I want to look at some compounds that have multiple bonds. Multiple bonds meaning double bonds and triple bonds. And we'll see there's a correlation between the type of bond and the bond lengths and the bond strengths. Why don't we first look at a carbon-carbon bond? And we'll have both single bonds and multiple bonds. All right. For a carbon-carbon single bond, you know that carbon typically requires 4 bonds, and we'll fill in the rest of the bonds with hydrogen. And I want to compare that to a carbon-carbon double bond. The way you count bonds, if you want to achieve 4 bonds, is count each line as a bond. So right now each carbon has 2 bonds, and I'll draw the other bonds as bonds to hydrogen. And then we have a triple bond. That means I'm going to put the 4th bond of each carbon, in this case also as a hydrogen. Now for bond, we'll do bond lengths. The bond length, and we're only looking at the CC bond, okay? That's a colon, that's not two electrons. But the CC bond length, and that will be, I'll use picometers. Let me put it down here actually. 1 pm, 1 picometer equals 1 times 10 to the minus 12 meters. Okay. Smaller than a nanometer, smaller than an angstrom. And for this carbon-carbon bond up here, it is 154 picometers. What is that? That's 0.154 nanometers. When we have a double bond, it gets shorter, and it goes to 134 picometers. And a triple bond gets even more short, 120 picometers. I'll explain briefly why the bond length drops as you add more bonds between the two atoms you're looking at. But before that, let's look at bond strength. This is the amount of energy needed to break the bond. Oops. And when I mean break the bond, I mean totally separate the two carbons. So you are cutting, for instance, for the double bond, you are cutting completely, so there's no interaction between the two carbons. For a single carbon-carbon bond, that is 348. Oh, I didn't tell you the units. Kilojoules per mole. Okay. So yeah, 6.02 times 10 to the 23 carbon-carbon bonds that are all single would take 348 kilojoules to break all of them. For the double bond, it actually jumps. It gets harder to break. It's harder to break. And then for the triple bond, 839. So what that number means is that out of these 3 examples, this is the strongest. And for the bond length, the triple bond is the shortest. And this is specific for the carbon-carbon triple bond. Okay. So with more electrons in between the two atoms that are being bonded, the distance becomes shorter and the strength of that bond becomes larger. Why is that the case? That's the case because the more the more bonding electrons in between the two atoms, the less repulsion there is between the two positively charged nuclei of the atoms. Or we'll just say positively charged nuclei. So take a look at that bond, triple bond between two carbons. There are six electrons in between the two nuclei of the two carbons. If we didn't have those electrons there, then yeah, we'll definitely have like charge repulsion. Yeah, like charge repulsion, or just simply charge repulsion between two like charges. But by putting those electrons in between those two nuclei, we sort of shield. We shield the two nuclei from each other. So you could think of it that way also. There's more shielding between the two positively charged nuclei. And it goes, I think logically, that as those two atoms get closer, due to the more shielding, the bond gets stronger. It's harder to separate. So this is also harder to separate the two nuclei from each other. Or you could just say separate the two bonds. Not the two bonds, but the two atoms. Okay. All right, let me show you a couple more examples. Let us do, yep, let's do oxygen, carbon-oxygen bonds. So for instance, if I have a carbon-oxygen single bond, and how do I fill in the rest of the bonds? Well, again, carbon, we learned from the bonding rules, requires 4 bonds, and oxygen requires 1 bond. Oh, sorry, 2 bonds. And oxygen has 2 lone pairs. This oxygen is neutral. How about a double bond between carbon and oxygen? All right, 2 lone pairs for the oxygen, and 2 more bonds to carbon to make 4 bonds to carbon. And then there is a case where you could have a triple bond. It's going to look a little strange because, how should I say this? This is going to be carbon monoxide. Carbon monoxide actually has a lone pair on carbon and a lone pair, yep, that's right, lone pair on the oxygen. Let's not worry about formal charge, but carbon monoxide has a positive charge on oxygen and a negative charge on carbon. Don't worry about that. We're focused on the single, double, and the triple bond between carbon and oxygen. The bond length, again, will be in picometers. Okay, they're all around the 100 mark, but we still see a general trend. As you go from single to double to triple, the bond lengths get shorter, but the bond energies get larger. And again, kilojoules per mole. This one's over 1,000. Okay. One more example, and then I have a few parting words before we are done with this video. How about some diatomic molecules? For instance, H2 versus N2. Oh, wait. Let's do oxygen. H2 versus O2 versus N2. All right, you should know your diatomic molecules. And if you want to draw the Lewis structures, oh, you should know the Lewis structures as well. For oxygen, okay, it's a double bond between 2 oxygens. For nitrogen, just double check. What am I double checking for? I'm double checking that the oxygens satisfy the octet rule, and I have the right number of electrons, right number of valence electrons, right? There's 6 valence electrons for oxygen, but we have 2 oxygens, so that's 12. 2, 4, 6, 8, 10, 12. Okay. For nitrogen, many of you know that it's a triple bond. Nitrogens have, in the neutral state, 3 bonds and a lone pair. Okay. I only have, I don't have the bond strength, but I do have the bond lengths, I think. I hope. I don't have the bond lengths. I do have the one for oxygen, O2, 121. What would you predict for this triple bond? I know they're different atoms, but in general, a triple bond will still be shorter, and this is 110. And the hydrogen-hydrogen bond is probably a little shorter than the carbon-carbon bond. Let me look it up real quick. I should have done this. I didn't realize I didn't have this. H. H bond length. Whoa. That can't be right. Yeah, that is alright. Let me find it. Oh, my bad. This is 74. So why isn't that longer? It's because, I'm glad we went over this example, because H is in the first period. We really should compare apples to apples. So nitrogen and oxygen are in period 2. Let me look up the bond length for diatomic fluorine, F2. F2. And now we can compare apples to apples, hopefully. They're different atoms, but at least they're all in the second period. F, O, and N. Let's see, F, bond length. There we go, 145. The bonds are getting shorter when we go from fluorine-fluorine single bond to oxygen-oxygen double bond to nitrogen-nitrogen triple bond. Okay, this is going to be a short video, but there is one last thing I want to discuss, because now that we have a good picture and several examples of single bonds, double bonds, and triple bonds and how they differ, there's a property called bond order. And I'm going to talk more about bond order in a future video, but I want to introduce it here. And it's very simple so far. A single bond has a bond order of 1. Double bond has a bond order of 2. Triple bond has a bond order of 3. What is the purpose of this? Why do we have to have a bond order where all it looks like we're doing is saying a single is 1, a double is 2, and a triple is 3? Why can't we just say single, double, triple? Because later we're going to see something a little bit unusual. We're going to see a 1.5 bond order. And there's a simple calculation to figure that out once we have all the Lewis structures. What does that mean? It's a bond between a single and a double. It has characteristics of both, or you could say it's the average of both. For instance, if I have a carbon bond being 154 and a double bond of 134, theoretically, you would think the 1.5 bond length would be what? Halfway, maybe 140, 144. Yeah, that's halfway, right? 144. And those do exist. You know, we even have examples of a 1.333 bond order. That's 1 1/3. Okay. So it's between a single and a double bond, but it's more leaning towards the single bond. There is a such thing as a 1.66 bond order. Okay. Thus far, the way we draw bonds, it's either a single bond, double bond, or triple bond. I'll show you in a future video, once we understand what the bond orders are, these fractional or decimal bond orders, how to draw those. Okay, it's probably something that is going to be new to a lot of you.